Okay guys, in this video we're going to be talking about Le Chatelier's principle, which describes the different ways in which we can affect the equilibrium of a chemical reaction. So we're going to be introducing perturbations on a equilibrium mixture, and then we're going to ask ourselves, in which way will the reaction react in order to get back to equilibrium? Okay, so that's this idea of stressing the equilibrium and then predicting the response of the system using Le Chatelier's principle. And so Le Chatelier's principle states that there's four ways in which I have broken down Le Chatelier's principle. Let's see. I think the first way we'll talk about is Le Chatelier's principle with respect to concentration. Whenever you change a reactant or product concentration for a system that's in equilibrium, what this does is this causes the equilibrium composition to change. We say that the reaction shifts. And so a shift towards the products means that the amount of products will increase and the amount of reactants will decrease. If we are to shift to the reactants, that means the amount of reactants will increase and the amount of products will decrease. Okay? So there's different ways in which you can push the reaction around. We also say to the right, meaning to the product side, or shift to the left, to the reactant side, just as a shorthand. And so here we're looking at, as an example, we're taking this reaction with carbon monoxide and hydrogen to produce methane and water vapor. What I wanted to point out is if you increase the concentration of a reactant, that is, if you add to the reactant, what that does is it pushes the reaction towards the products. So it shifts to the product side. So if you increase the concentration of a reactant, it's going to drive or push the reaction a little bit more to the products. So if you were to add carbon monoxide, the amount of carbon monoxide in the mixture would increase, the amount of hydrogen would decrease a little bit, and the amount of methane and the amount of water vapor would increase. Okay, so dumping in some carbon monoxide is going to push the reaction a little bit to the product side. Another way you can do that would be to siphon off one of the products. So for example, suppose that you siphoned off some of the methane here. That would cause the methane concentration to decrease, and the system would respond, that is, it would try to get back to equilibrium by decreasing the amount of the reactants a little bit in order to compensate for the change that you introduced. So it would make some water vapor in addition to a little bit of methane to compensate for the amount of methane that you took. So you can either add a product or you can either add a reactant or remove a product, and that will shift the reaction towards the product side. Alternatively, you could add a product. So you could add water vapor to this reaction mixture, increase the concentration of the water vapor in the reaction mixture. What that's going to do is it's going to push the reaction towards the reactant side. So you'll dump in some water vapor, you'll find that the amount of methane is going to decrease a little bit, and the amount of carbon monoxide and the hydrogen gas is going to increase by a little bit. Okay, so a shift towards the reactants whenever you add a product. Or you could remove a product, you could remove a reactant. So for example, we could siphon off some of the hydrogen gas. That has the effect of pulling the reaction towards the reactant side. So if you siphoned off the hydrogen gas, that would cause the amount of carbon monoxide to increase a little bit, and the amount of methane gas and the amount of water vapor at equilibrium would decrease. Okay, so you can push the reaction or pull the reaction either way by adding or removing a gaseous or aqueous reactant or product. I want to point out that for heterogeneous reactions, adding or removing a pure liquid has no effect on the equilibrium composition. And we've discussed that previously. In the previous video, we talked about how solids and liquids have constant concentrations, and therefore they don't appear in the equilibrium constant expression. Similarly, when you add or remove a pure liquid or pure solid, it doesn't affect the equilibrium equilibrium composition, so there will be no effect by adding or removing a solid or liquid. You want to watch out for that. I also wanted to point out that there's a limit to how much you can push a reaction around. So what I have here, this is the reverse of a combustion reaction. Okay, so here we're burning methane. If you go the other way, you're burning methane and oxygen to produce CO2 and hydrogen. If you imagine turning the reaction around, this reaction has a very small equilibrium constant, which means at equilibrium you have almost exclusively, essentially you have only reactants. Okay, so CO2 and water vapor are very stable together. They are not going to spontaneously form methane on their own. And adding a little bit, increasing the concentration of the CO2 isn't going to produce any methane. And that's because the equilibrium constant is just so small that there's nothing you can really do to affect it. Okay? So this reaction is effectively a one-directional reaction going towards the reactants. Not all reactions can be shifted. So that was Le Chatelier's principle with respect to concentration. I want to do a couple of examples here on the page. And, it's easy to just say, oh, you can add or remove a product. But then the real question is, how do you add or remove a product? Well, adding stuff is really not that complicated. You just supply more of what you have. But how do you remove a species from a chemical reaction mixture? That's the question I wanted to address with you right now. So let me give you an example of an equilibrium reaction. So we'll consider a dissolution reaction involving aluminum hydroxide. Aluminum hydroxide is not very soluble in water, but it will dissolve just a little bit. And so it's easy to saturate an aluminum hydroxide solution. And what I want to ask you is, can you think of a way to increase the solubility of the aluminum hydroxide? How would you get more of the aluminum to dissolve? Well, according to Le Chatelier's principle, one thing you could do would be to pull out one of the products. Right? So what if you could pull out some hydroxide? Well, in principle, that's going to shift the reaction to the right. That would make the aluminum hydroxide more soluble if you could somehow decrease the concentration of the hydroxide ion in solution. Well, how do you do that, though? What can you do to pull ions out of a solution? Well, what you can do is you can add something that's going to react with those ions. So this is hydroxide, and you should hopefully remember from Chem 120 that if you add an acid, I don't know, let's suppose that we're adding hydrochloric acid. Okay, when hydrochloric acid is in water, it forms hydronium ions. Okay, so hydrochloric acid essentially consists of hydronium and chloride ions. Whenever you combine the hydronium and the hydroxide, you get a neutralization reaction occurring. Proton is donated, and you make water. So by adding hydrochloric acid to a solution, a saturated solution of aluminum hydroxide, what it's going to do is it's going to consume the hydroxide. Okay? So you'd be decreasing the hydroxide ions in the solution. That would in turn make the aluminum hydroxide more soluble. Okay? And so it would increase the concentration of aluminum ions in acidic conditions. Okay? So this is the way you need to think as a budding young chemist. What can I do to my solution to make it do what I want it to? Let's do another example. Let's consider a saturated solution of silver sulfate. Should be 2 minus. Okay, so this is another dissolution reaction. Again, what I want to do is I want to increase the solubility of the silver sulfate. How can I do that? Well, you can't add more silver sulfate, right? Because that's a solid. Okay, that conflicts with this rule here. Adding a pure solid won't affect it. So you can't add more reactant. You have to pull out one of the products here. Let's pull out the silver. How would I pull silver ions out of a solution? Okay. Well, the way to do it is to add something that will form a precipitate with the silver. Okay. So we know that from our solubility rules that most halide compounds are soluble. However, there are some exceptions, and silver chloride is one of those exceptions. So, for example, you could add some sodium chloride solution, right, which we know consists of sodium ions and chloride ions. So when you pour into this beaker containing this equilibrium reaction, when you pour in some sodium chloride solution, you're going to be adding chloride. And what will happen is the silver will form a precipitate with the chloride, and it's going to pop out as a solid. Okay? And so this precipitation is going to decrease the concentration of the silver ion in solution. That'll in turn increase the solubility of the silver sulfate. Okay, so that's another way that you can manipulate the amount of a reactant or product. Here we did an acid-base neutralization reaction. Another way you can do this is through precipitation reactions. Okay, so that's Le Chatelier's principle with respect to concentration. Let's talk about temperature. In fact, we've already covered this in the first chapter that we looked at when we were doing solutions. We talked about solutions that when a solution forms, it's endothermic. Like, so for example, if you dissolve an ionic compound in water, is it an endothermic change or is it an exothermic change? And depending on which it is, you can use the sign of delta H to predict whether or not the solubility of a given ionic compound will increase or decrease when you change the temperature. So here are the here it is. Here's the slide. So there's two cases. Okay, so you can have a reaction, an equilibrium reaction. That is, we'll do the endothermic case first. So delta H is greater than 0 for this reaction. Here you would have your heat. You could think of your heat as a reactant, and we associate that with the temperature. For the second case, we'd consider an exothermic reaction. Delta H is negative. You can think of the heat then as a product, and we associate that with the temperature term. Okay, so now that we've put this heat term into the equation, it's based upon the sign of delta H. When delta H is positive, I put the heat term on the reactant side. When delta H is negative, it's exothermic. I put it on the product side. Heat is a product. Now that we've got the heat term in there, we can use Le Chatelier's principle, this sort of teeter-totter, push-pull approach. For an endothermic reaction, if you increase the temperature, that is going to push the reaction towards the products. If you cool the endothermic reaction down, that's going to pull you back towards the reactants. The same technique works for the exothermic reaction, it's just that you get opposite conclusions. If you increase the temperature of the exothermic reaction, it's going to push you to the reactant side. If you cool down the exothermic reaction, it's going to pull you back to the product side. Okay, so those are the two rules that I have on the slide here. Okay, so that's Le Chatelier's principle with respect to temperature. Here, the more complicated case, or the more complicated version of Le Chatelier's principle has to do with pressure changes. It's not too bad, but let's try discussing it here. So first, I want to differentiate between different types of pressure changes. So the first type of pressure change that we're going to look at is a pressure change due to changes in volume, which is particularly important for gaseous reactions. So for this equilibrium reaction here, we've got, let's write out the Kp. It would be the partial pressure of the methane times the partial pressure of the water vapor divided by the partial pressure of the carbon monoxide and the partial pressure of the hydrogen cubed. So here's our Kp expression. Now we can change the pressure associated with the volume change. We can do two things. We can decrease the volume of the container. So if you take your volume and you squeeze it down, okay, that's going to cause the partial pressures of all of the gases inside to go up. And so the system is going to respond by making fewer moles of gas. Okay, let me say it again. So you take your gaseous container and you squeeze it down. Okay, that causes the partial pressures of all of the gases to go up. And as a consequence of that, the system responds by making fewer moles of gas. Okay, so which way the reaction will go will depend upon which side has more or less moles of gas. In this particular reaction, I'll go ahead and write it out. We see that the product side has fewer moles of gas, and so what we can do is I can add a PV term here. Okay, so this is how will we use Le Chatelier's principle for pressure changes associated with volume changes. Put the PV term on the side that's got more moles of gas. Okay, and so now what happens is you're going to be increasing the pressure by decreasing the volume. What that's going to do is that's going to push the reaction away from the side with more moles of gas. Okay, so you can use the visual trick to help you in this case as well. What's the opposite thing you can do? Well, instead of squeezing the system, you can expand the volume. Okay, so if you expand your volume, that causes the partial pressure of all of the gases to go down. That would be like pulling the reaction to make more moles of gas. Okay, so that's how the system would respond. If all of the partial pressures go down, it's like there's not enough gas in the system, and so to compensate for that, the system will produce more moles of gas. For this reaction, it's going to shift you to the left. So it depends upon which side of the reaction has more moles of gas. In this case, the reactants did, but you can easily imagine a reaction where the products had, I don't know, I'll make this 3 and we'll make that a 1, where the products have more moles of gas. Okay, here, if you were to squeeze the volume down, okay, that would cause the partial pressures of everything to go up. The system would respond by making fewer moles of gas. So using this PV term here, if you increase the pressure by decreasing the volume, what that's going to do is it's going to push you towards the reactant side. Conversely, if you made the volume bigger, that causes the partial pressures to go down. The system responds by making more moles of gas. That would be like pulling, in the Le Chatelier's principal balancing act, that would be like pulling towards the product side for this particular reaction. Okay, so that's how the pressure volume works for gaseous reaction. What I'll point out as just a final thought on that is that if the number of moles of gas on each side of the reaction is the same, then the pressure effect is, there isn't a pressure effect using these volume changes. So you have to have a difference in the number of moles of gas in order for the pressure change to have an effect. There's another way to change the pressure in a reaction mixture. You could also add an inert gas. That is, you can pump in something like helium or argon, something that won't react with any of the species. And what that's going to do is it's going to increase the pressure inside the vessel. Now there's two ways in which this can be done. Either you've got a rigid vessel, a rigid container, in which case adding the inert gas will have no effect on the equilibrium mixture, and that's because the volume cannot change if the container is rigid. So you can pump in all the helium you want. That's not going to change the partial pressures of any of the gases participating in the chemical reaction, and therefore no effect will be made on the equilibrium composition. However, if you have a flexible vessel like a balloon or something like that, and then you've got a reaction going on inside this balloon, and you start increasing the volume of the container by pumping in inert gas, what that's going to do is it's going to decrease the partial pressures of all of the gases participating in the mixture, in the reaction mixture. And that's going to, in turn, cause the equilibrium system to make more moles of gas. Okay, so that's the rule for inert gases. If the container is rigid, there's no effect. But if the container is flexible, when you pump in an inert gas, that increases the volume, which decreases the concentrations of the reactants and products. The equilibrium shifts to make more moles of gas. Okay, and so these rules you want to practice. In my opinion, you'll need to practice. Oh, I got one more rule I forgot. The effect of a catalyst. The Chatelier's principle for catalyst is catalysts have no effect on the equilibrium for a reversible reaction, and I can point out why that is. So let's go back to these potential energy diagrams that we covered in kinetics. Okay, so right, you've got an activation energy in this way, you've got an activation energy here. The activation energy going in the forward direction is connected with the forward rate constant. The activation energy in the reverse direction is associated with the reverse rate constant. The equilibrium constant is a ratio of the forward over the reverse rate constant. That's what we talked about in a previous video. When you add a catalyst, what it does is it decreases the activation energy of both the forward rate constant and the reverse rate constant. So as a consequence of that, both of these numbers are reduced by the same amount, and hence the equilibrium constant doesn't change. Okay, so the equilibrium constant, which is related to the equilibrium composition, does not affect or is not affected by the presence of a catalyst. The catalyst just speeds up how quickly you get to equilibrium, but it does not actually affect the equilibrium composition. Okay, I wanted to make one more important point about this section, and that's the rationale behind it. I probably should have said this stuff as I was going. Let me see if I can. Let's talk about why. Why does Le Chatelier's principle for concentration work? Well, remember our Q and K comparison problem, right, where we were playing around with this. We were using this device to help us predict which way the reaction needs to go to reach equilibrium. You know, if the reaction quotient is smaller than K, then you need to go towards the products to reach equilibrium. If the reaction quotient is greater than K, then you need to go back towards the reactants to reach equilibrium. When you've got a system at equilibrium, effectively your Q equals K in that moment, right, when you're at equilibrium. Well, what happens if you dump in products, right? Your equilibrium, let me do it this way, products, equilibrium, reactants, equilibrium, okay? So when you add in a product, let's say, so it's like to this reaction, let's say I'm adding in methane. What that does is it means that Q will no longer equal K, like when you add something in or when you take something out. In the case where you add in a product, what that does is it means that you're suddenly changing the value of Q. It's no longer equal to K, and you're increasing its numerator, which means that Q is now going to be larger than K, And in order to get back to equilibrium, the reaction needs to go back towards the reactants. Conversely, if you added in a reactant, like you have your system at equilibrium, where Q equals K, you dump in some reactant, that means the denominator is going to be suddenly larger than it should be to be at equilibrium. And that's going to make Q smaller than K. And in order to get back to equilibrium, the reaction needs to go to the right. So when you add or remove a reactant or product, what you're really doing is you're changing the value of Q, and the system needs to respond in order to get back to equilibrium. It's a little bit different when you're talking about Le Chatelier's principle with respect to temperature, because changing the temperature doesn't affect the concentrations of any of the species. What changing the temperature does is it changes the value of the equilibrium constant itself. Okay, so you have your system at a given temperature at equilibrium, Q equals K, then you suddenly change the temperature of the reaction. Well, that's going to either increase or decrease the value of K relative to Q, and it's going to put you in one of these situations, but not because Q changed, because K changed. And the way K changes depends upon the sign of delta H. And the little rule that I've shown you here, there's one for endothermic, there's one for exothermic. It's just putting the Q on the other side. Doing this trick for endothermic and for exothermic helps you get the rule correct. Okay. For the volume changes, the pressure volume changes, again, that changes Q, not K. K is constant for a given temperature. When you make a volume pressure change, that changes the value of Q relative to K. And so the system needs to respond to get back to equilibrium depending on whether Q became larger or smaller than the equilibrium constant. All right, well, that's all I wanted to share with you on this particular topic. I think what I was about to say was that you really need to practice these rules, and I don't know that the sapling homework gives you enough practice for that. And so what I suggest you do is you work additional problems from the end of the chapter of the textbook. There's a whole bunch of Le Chatelier's principle problems there, and I suggest you go through as many as you can to help you learn the rules, because this will be a dominant topic on the exam. So with that, I will go ahead and stop this video, and we'll do some calculations in the next one.